All right, today we're going to peel back the surface of our planet to really understand the huge forces that are constantly moving continents, building mountains, and, unleashing some of nature's most powerful events. So let's dive right in. But before we take a journey to the center of the Earth, let's start right here, on the surface, with the really dramatic effects that we can actually see and feel. So, what you're looking at here is the energy from the 2004 Indian Ocean tsunami, just radiating across the entire globe. It all started with a massive undersea earthquake that displaced an unbelievable amount of water, sending these waves thousands of kilometers across the ocean. I mean, this is the kind of raw power we're talking about, the kind that can reshape our world in just an instant. And that really brings us to the big question, right? What in the world is going on deep beneath our feet that could cause something so incredibly powerful? Well, to find that answer, we have to look at the very structure of our planet. Okay, so let's take that journey inward. We're going to explore the layers of the Earth to find the engine that's driving all of this incredible activity. You probably remember this from school, right? Our planet is made of several layers. We're living on the crust, which is super thin, relatively speaking. Beneath that, you've got the huge mantle, and then way down at the center is a super hot core. But the real key to our story, the part that makes everything happen, is in a very specific zone between that crust and the mantle. And that layer is called the asthenosphere. It's this section of the upper mantle, and it's not quite solid, but it's not quite liquid either. The best way to think of it is like extremely thick, hot tar. This right here, this is the true engine room of our planet. So here's the deal. The incredible heat coming from the Earth's core creates these really slow but powerful churning motions in this semi-molten rock. We call these convection currents. Now, the solid crust we live on is broken up into these giant pieces called tectonic plates, and they're basically just floating on top of this moving layer, getting carried along like luggage on a massive global conveyor belt. And it's where these massive plates actually meet that all the action happens. These plate boundaries are the hotspots for most of the tectonic activity on Earth. So let's break down the three main ways these plates interact. First up, we've got constructive boundaries. You can basically think of these as the planet's creation zones. At these spots, those convection currents we talked about are pulling two plates away from each other. As they separate, hot magma from the asthenosphere rises up to fill the gap. It then cools and hardens, creating brand new crust. This is literally where the Earth makes more of itself. And here is a perfect real-world example. This is Iceland, a country that is sitting right on top of the Mid-Atlantic Ridge. So you are literally looking at the gap between the North American and Eurasian plates. This is seafloor spreading that you can see on dry land, and it's exactly why Iceland has so many volcanoes and these incredible rift valleys. Okay, next up we have the complete opposite. Destructive boundaries. Because it makes sense, right? If new crust is being made in one place, then old crust has to be getting consumed somewhere else. At these boundaries, plates are on a collision course. What happens when they hit really depends on what kind of plates are colliding. A lot of the time, a heavier, denser oceanic plate will slide underneath a lighter continental plate. We call that process subduction. But in other cases, two continents might just smash directly into one another. And this right here is the absolutely spectacular result of one of those continental-continental collisions. The Himalayas were formed when the landmass of India, which was traveling north, just slammed into the Eurasian plate. Since neither plate was really heavy enough to sink or subduct, the crust had nowhere to go but up. It buckled, it folded, and it created the tallest mountain range on the entire planet. And for our third and final type, we have boundaries where plates aren't creating or destroying crust. Instead, they're locked in this high-stakes sideways dance. At a conservative boundary, two plates are just grinding past each other horizontally, so no new crust is made, no old crust is destroyed. But, and this is a big but, the immense friction means the plates often get stuck. They snag on each other, and they build up incredible amounts of stress, sometimes for hundreds of years. And a perfect and probably the most famous example of this is the San Andreas Fault in California. This is the boundary where the Pacific plate is sliding past the North American plate. When all of that pent-up stress is finally released in a single moment, the result is a massive, powerful earthquake. Okay, so let's do a quick recap. At constructive boundaries, plates pull apart to create new land, giving us things like mid-ocean ridges and volcanoes.
At destructive boundaries, plates collide, which builds huge mountains or carves out deep ocean trenches. And at conservative boundaries, plates slide past each other, storing up all that energy for major earthquakes. 3 different movements, 3 very different results.
So now that we've got the mechanics of these boundaries down, let's zoom out and see how this all fits together to shape the entire planet. And this is where it all just clicks. The lines you see on this map show the plate boundaries we've just been talking about, and the dots? Those are the locations of major earthquakes. The pattern is it's undeniable. The vast majority of earthquakes and volcanoes happen right along these boundary lines, especially in that massive arc around the Pacific Ocean that we call the Ring of Fire. This map, right here, is the theory of plate tectonics in action. It's the whole story in one image. And you have to remember, these movements are not new. They've been happening for hundreds of millions of years, and they have completely reshaped the face of our world. Continents have drifted apart from one single supercontinent, Pangaea, to form the oceans and the land masses that we all recognize today. You see, the world map isn't a static picture. It's just a single snapshot in a very, very long movie. When you get down to it, the world we live on is constantly being unmade and remade from within. The ground beneath our feet isn't solid or stable at all. It's this dynamic, ever-shifting mosaic. And it really makes you wonder, doesn't it? What will our planet even look like millions of years from now?